Hello, good friends. Today, we're going to unpack the important topic of advancing reasoning in large language models, inspired by a groundbreaking study titled Training Large Language Models to Reason in a Continuous Latent Space from FAIR at Meta and UC San Diego. Now, as many of you know, large language models, or LLMs, have revolutionized how we interact with machines. They've shown remarkable abilities in understanding and human language, primarily operating within what's known as the language space. Traditionally, these models use a method called chain of thought, or COT, where they reason step by step in natural language to solve complex problems. However, the researchers at FAIR and UC San Diego argue that this language-centric approach might not always be the most efficient or effective way for machines to reason. Imagine this: when humans reason, our brains don't exclusively rely on language. Neuroimaging studies have shown that the language centers of our brains often take a back seat during various reasoning tasks. This suggests that while language is a powerful tool for communication, it's not always the primary driver of our reasoning processes. Translating this insight to LLMs, the researchers propose that confining reasoning to language may impose unnecessary constraints, where many tokens are used merely for textual coherence rather than actual reasoning. Enter Coconut, short for Chain of Continuous Thought. Unlike COT, Coconut operates in an unrestricted latent space, tapping into the last hidden state of the LLM as a representation of the reasoning process. Instead of decoding this hidden state back into words at each step, Coconut feeds it directly back into the model as the next input embedding. This seamless loop allows the model to reason more fluidly, akin to how humans think without always verbalizing every thought. One of the most fascinating findings from the study is how Coconut enables what the researchers describe as a breadth-first search in reasoning. Traditional COT tends to commit to a single path of reasoning, which can lead to dead ends, especially in complex problems that require revisiting and backtracking. In contrast, Coconut's continuous thought can encode multiple potential next steps, allowing the model to explore various avenues simultaneously and discard the less promising ones as it progresses. This mirrors a more dynamic and flexible problem-solving approach, enhancing the model's ability to handle intricate logical and mathematical reasoning tasks. The experiments conducted by FAIR and UC San Diego are quite telling. Using datasets like GSM8k for math reasoning and ProntoQA, along with the newly introduced ProntoQA for logical reasoning, Coconut consistently outperformed traditional COT methods. Not only did it achieve higher accuracy, but it also did so with fewer tokens, making the reasoning process more efficient. For instance, in tasks that require substantial planning and backtracking, Coconut not only navigated these challenges more adeptly, but also reduced the computational overhead by generating fewer reasoning tokens during inference. But why does reasoning in a latent space make such a difference? The researchers delve into this by analyzing the latent reasoning process as a sophisticated search tree. Coconut's ability to maintain multiple potential reasoning paths allows it to prioritize more promising nodes while pruning away the less relevant ones. This method enhances the model's planning capabilities, ensuring that it remains focused on viable solutions without getting bogged down by less fruitful avenues. Moreover, the study highlights that increasing the number of continuous thoughts, essentially the different potential paths the model can consider, further boosts both the accuracy of the final answers and the robustness of the reasoning process. Case studies within the research demonstrate that Coconut effectively eliminates incorrect options and hones in on the correct answers with greater precision and reliability. The implications of this research are profound. By shifting the reasoning process from a language-constrained framework to a continuous latent space, we open up new possibilities for how machines can think and solve problems. It suggests a future where LLMs are not just powerful language generators, but also sophisticated reasoning engines capable of more human-like problem-solving. Looking ahead, the researchers envision further refinements and scaling of latent reasoning methods. One promising direction is pre-training LLMs with continuous thoughts from the outset, potentially enabling these models to generalize their reasoning abilities across a broader spectrum of scenarios. This could lead to more adaptable and intelligent systems, capable of tackling a diverse array of challenges with greater efficiency and effectiveness. In conclusion, the Coconut paradigm introduced by FAIR at Meta and UC San Diego represents a significant leap forward in the field of artificial intelligence. By reimagining how large language models reason, moving beyond the confines of language to embrace a continuous latent space, we not only enhance their current capabilities, but also pave the way for more advanced and versatile machine reasoning systems in the future. As we continue to explore and build upon these insights, the potential for even more sophisticated and human-like AI becomes increasingly attainable. Thank you for joining me today as we delved into this exciting development in AI research. Until next time, keep pondering and stay curious.